Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's about time to start this afternoon session. My name is Juichi Tsuji, and chairing this session. So in the field of medical science or biology, we have not only huge amount of data, images scattered around in different institutions, hospitals, and so on, but also a myriad different types of text in terms of medical record, scientific publications, as a scientific heritage. So in order to advance the science in this field, it is really necessary to correlate those huge amount of data and text in a coherent manner. This is a kind of a new challenge for eScience. So this session will address those issues by 5 speakers. Dr. Simon Mercer, Microsoft Research, Professor Lai, the president of China Pharmaceutical University, Dr. Chan, Dr. Poon from Microsoft Research, and Professor Hogan, Queensland University of Technology. So we have 1 hour and half minute, half an hour for this session, and basically 4 different talks. So we don't have much time for the speakers. So I just give this place to the first speaker. The first speaker is Dr. Mercer of Microsoft.
Good afternoon. I'm going to talk very quickly. I'm only going to give you a 10-minute talk today. And the reason is because I don't really have any results to report, but what I'd like to do is I'd like to tell you about a project that we've started in the Microsoft Research Connections team, the same team that organizes this workshop. And I'd like to invite you to participate in it if it's of interest to you to do so. Now, for those of you who heard Kenji Takeda's talk this morning about what is eScience, you'll have heard something that he said there, which is particularly relevant here. And that was that it is part of the goal of the Microsoft Research Connections team to build software which is applicable in many different areas of eScience. And I'm about to describe to you some examples of that, which, although I'm applying it in the area of medical imaging, has much broader application and may be helpful to you all. The software I'm going to discuss here is also freely available under an open source license for any of you to use for academic purposes. So, medical imaging. One of the things that people don't realize is just how much data is actually out there in terms of medical images. Medical images are a real problem to store. Anybody who goes to a hospital will have CT, MRI, histopathology, a range of other types of images collected about them. And by some estimates, it's the single largest data source, the single largest digital data source that humanity collects. But it's worse than that. It's also legally protected because it's medical data. And it has all sorts of legal constraints on its use because it can identify people or it can affect your privacy and other things. So it's very hard to get a set of medical data that you can easily share with people. And so what we're interested in doing is trying to free up the stream of medical data right the way from the patient all the way through to the development of better medical imaging algorithms. And the reason why we care about that is we believe fundamentally that better algorithms, the pace of research is accelerated by having more data more freely available to a larger number of scientists so that they can analyze it, they can compare their results, and they can develop new hypotheses hypotheses and new algorithms to solve new challenges. And so everything I talk about here related to medical imaging could also apply, of course, equally well to natural language processing or to any other area where one or more scientists wish to compare the information that they have between them to figure out who has the best techniques for analyzing a certain set of data. So, the reason why we were interested in this actually comes from the development of the Kinect, the Microsoft sensor that you can control a gaming device, for example, with. When the algorithms that underlie Kinect were developed, we required a very large data set of body position images so that we could train the algorithms to detect the body position of someone wishing to play a game. And we had tens of thousands of such images available to us, but we found that when we ran this training set, it wasn't really succeeding in training the algorithm as well as we would like. So what we ended up doing, actually, is creating a means of generating large amounts of synthetic body position data. And as soon as we broke down the barrier that limited us, instead of just having tens of thousands of images, to having millions of images to train our algorithms, we were capable of producing extremely good algorithms and producing the Kinect, which, of course, has been a highly successful product today. So the goal here, as we see it, is if you free the data, you accelerate the research. And in the area of medical imaging, there's 3 different stages. And if you see my slide here, you'll see there's a yellow band across the top indicating we can think of medical imaging as having 3 different stages which are relevant to us here. The first is acquisition, actually collecting data. The second is annotation. Okay, so you've got tons and tons of data. What are you going to do with it? You're going to need new tools because you have more data that you need to analyze now. And the third is collaboration. It's all very well having a wonderful set of medical data, but if you're the only person that can access that data, you can't use it to compare the success of your algorithms with the success of other people's. Very often in the medical field, you will find scientific papers that describe extremely good algorithms. And if you want to download the training data set so that you can compare and verify that the performance of those algorithms, you'll find that that's very hard to do, perhaps because the data set isn't publicly available, or perhaps because it's available only for research purposes. So you don't go to a website and you download the data. Instead, what you have to do is phone up the researcher and ask for their permission and maybe fill out a form. That's a barrier to research. We want to make sure that data is freely exchangeable, and that's what collaboration is about. So, in terms of data acquisition, I won't really talk about that because I have a very limited amount of time today. Please feel free to talk to me this evening or talk to me after the session. I'll be happy to talk about our approaches to data acquisition, which will help streamline the process. Data annotation, though, is interesting because we have a tool which enables the semi-automated segmentation of medical images. In other words, we have a tool that if you need to create a set of ground truth data which you know is correct so you can train your algorithms appropriately, then what you need to do is take each medical image and manually draw around the different structures on that image, a process called segmentation. The problem with doing that is that in order to do this correctly, you need to be a medical expert. And medical experts are rare, and they are very often quite expensive. So it's very hard to create large, well-annotated data sets to train your algorithms. Now, I'll show you in a minute GEOS, which is one of the tools that we've created to deal with that. If I just move on here, here's a slide. I'm afraid it's not very readable from there. But let me tell you about it. GEOS uses geodesic image segmentation, an algorithm which essentially the way it works is, as a user, if you have the image in front of you, say of a heart, then you take a paintbrush and you mark a piece of the heart. Any piece will do, it doesn't matter. Then you take a second brush and you mark an area which is not the heart. And then you push a button. And everything else happens automatically. For a 3D CT volume, for example, it will detect all of the heart in one layer, then move to the next layer and detect all of the heart, and so on, until it's filled out a 3-dimensional view of the heart. And it does it all automatically. We've run this algorithm, we've actually shared this application with radiologists who are practicing physicians. And they say that it accelerates the time it takes them to annotate a medical image from 1 hour to 1 minute. Now, you can take that literally, or you could just regard it as, at least an order of magnitude time saving, which is quite remarkable. Now, it's exactly this kind of time saving that you need. If you've got a human in the loop to generate your large annotated medical data set, quite clearly you need to find ways of making that human more efficient, otherwise you can't generate enough data to train your algorithms. But let's imagine you've succeeded. Let's imagine you have your data, you've generated a large, well-annotated data set from that data. What do you do next? Well, you don't push the button and move forward 2 slides, that's for sure. Okay. The next stage, the stage of collaboration, is CoderLab. CoderLab is a web-based, actually a cloud-based platform for the analysis of medical images and for the comparison and comparative benchmarking of medical image analysis algorithms. What you can do is you can run a competition if you wish to do so. If, for example, I have an algorithm which is really good at recognizing the heart in medical images, it can do it automatically. And let's say someone else has an algorithm which can also recognize the heart. My algorithm, I believe, is 85% accurate. Their algorithm, they believe, is 90% accurate. Well, in order to compare the algorithm and know which one of us is correct, what we need is a common set of data and a set of parameters where we know how we're going to evaluate the data properly. In other words, a set of agreed metrics. Once we've got the set of data and the set of agreed metrics, I can run my algorithm and get some results. They can run their algorithm and get some results on the same data. And now we can determine who has the better algorithm. These competitions are quite standard in machine learning, quite standard in the medical imaging community today, and CoderLab is a platform that supports exactly that kind of competition, so that many different groups can collaborate on a common data set and actually determine who is doing the best job of image segmentation, learn from each other, discuss the results, and share the algorithms as well. There's a workflow system built in here, there's various other things I don't have time to talk about, but I would encourage you to visit the website that we have, which is research.microsoft.com, Microsoft Research, of course, /medimaging. If you go there, you'll find links to the GEOS application that I showed you earlier, which is freely available for academic use, so long as you don't diagnose patients. It's prohibited to do that. And also you'll find details of CoderLab, and you'll be able to go and visit a CoderLab instance and take a look at it. And try uploading your own data, building competitions, and if you really like it, please come and talk to us, because it's an open source project, and what we're doing is we're building it and extending it with the help of other academics, because at the end of the day, Microsoft does not know what medical image analysis people need as well as the medical image analysis people do. So it's far better for them to build the features that they need with our help, rather than we build the features without scientific input. So the whole idea of this is it's not all on the Microsoft platform, it's freely shareable, and it's open source. So we're trying to encourage a community to build around medical imaging to accelerate algorithms for everybody. Okay, that's my talk. Thank you very much.
Any questions or comments?
Can you explain what synthetic data is?
Yes, I didn't really cover that point on the slide. There are a range of approaches to generating medical images synthetically. There are a number of algorithms that exist today that will create believable medical images, but they're not very accurate, we believe. And so at the moment what we're doing is we're working with Addenbrooke's Hospital in Cambridge in the UK. Actually, we've applied for some funding for this. I believe we will be successful shortly. To hire a postdoc to use a very large set of radiological images that have been collected at Addenbrooke's Hospital to train an algorithm which will emit synthetic images of the brain, actually, is our main interest at the moment. The idea is if we can actually create millions of medical images, rather than simply be limited to tens of thousands, perhaps, that you would collect from real patients, then we would succeed in our goal of liberating the data and making much larger training data sets for people to build better algorithms. Did that answer the question?
Okay, any other questions or comments? For this kind of initiative, the community involvement is really needed. So we are welcome for your participation. Go to the website to see the detail. Thank you very much.
Thank you.
So the next talk is a joint talk by Professor Lai and also Dr. Eric Chan.